Hello, my name is Pedro Ramalhet, and I'm here to talk about efficient algorithms for persistent transactional memory. This is joint work with Andrea Correia and Pascal Felber at University of Neuchâtel. We're going to assume some knowledge about Intel Optane persistent memory. This is byte addressable memory, and we're going to talk a little bit about the models that we used and the design that we're aiming for. Just like there is a memory model for programming with atomics and concurrency, there are also persistent models when you want to work with persistent memory. The one that we chose is the one by Israelevitz, Mendes, and Scott, and it defines three APIs for programming interacting with the persistent memory. That's the PWP, the pfence, and the psync. The PWP is a persistent write-back. It's a flush of a cache line, and it's ordered with respect to previous stores on that same cache line. The pfence is an asynchronous ordering fence. And then there's the psync, where there's synchronous ordering. Now, the difference between the pfence and the psync is subtle, but it is important. When you do a psync, you're guaranteeing that the data that you wrote before to persistent memory is now persistent, it's durable, it has reached the durable storage. While with pfence, you're just enforcing ordering amongst the different writes accompanied with cache line flushes. We also use the PCSO model by Cohen et al., which defines for x86 that stores to the same cache line are ordered. So you don't know when they'll reach the persistent storage unless you do the psync, and the flush for all the modified cache lines. But you do know that if W has been written to a cache line before X, then if you see X, for sure W has reached it before on the same cache line. An important detail about Optane DC persistent memory is that the lower the number of flushes that a certain algorithm executes, the faster it will be. So this means that if we want to execute fast transactions, we should strive for an algorithm that reduces the number of flushes as much as possible. And interestingly, for random writes, this metric is pretty much linear with the number of flushes, of PWPs. So we expect that if we design algorithms that reduce this number of flushes, then we get a linear improvement on the performance. So what are the different ways to obtain durable transactions in persistent memory? There are 4 ways to do durable transactions. The first one is undo log, and in undo log what you do is you have a persistent log and you keep there the original data before you actually modify it. And this is the case of techniques like pmem-obj in PMDK. At the end of the transaction, you clear the log, and that's it. You can commit safely. In read log, you also have a persistent log, but it works the other way around. First, you do the writes, the modifications on the persistent log, and at the end of the transaction, you reapply those modifications over the original data. All of this has to be made with fences at the right place. Examples of this technique are Mnemosine and OneFile. Then there's copy on write, sometimes called shadow copy, and in shadow copy, you usually have a pointer or a logical pointer, and when you want to do a modification, you create an entire replica of your data with these modifications, and then you do a single pointer swap with flushes and fences to indicate that the new data is the next one. And on shadow data, it's kind of similar like copy on write, but it's not the same thing because you keep 2 replicas the whole time and you keep them up to date. First, you apply the modifications on one of the data of the replicas, then you toggle the pointer, then you apply the modifications on the other replica. The next time you toggle the pointer in the opposite direction. Let's start with a small example for undo log. Suppose we have a short transaction where all we do is a equals 1 and the original data was 0. So we keep on the log before executing this instruction a equals 1. We keep on the log the address of a and the value that it was written on a. That's what all the code on the right side does. You need to flush and fence the contents of the log. You need to update the size of the log, and then you need to write the new data a equals 1 and finally flush it. If then you do b equals 2, again, you save the value of b, which was 0. In the log, you flush, you fence, you increase the size of the log, you flush and you fence, and then you update the actual location of b with the new value, which is 2. And if you want to do c equals b plus 1, you just read directly from b, and again, you do the same thing. Overall, you can execute this transaction using 8 pfence instructions and 10 flushes. Okay, so even though you modify just 3 variables, you need to do 8 fences and 10 flushes. For redo log, first you just write the new value on the log and you don't actually modify anything at the address of A. And you flush the log there or at the end of the transaction. You do again the same thing for the next instruction, but now C has a dependency on B. It needs to read the value of B, and it cannot read the actual value, the current value of B, because that is 0. So it needs to read from the log, do a lookup on the log to see if there's any entry for B, and then it can write the new value in the log itself. And at commit time, we can copy, we can in one shot update the value, the size of the log, and then flush the entire log, do the modifications, and in actual memory, flush them and order them. The end result is we do 8 flushes and 4 fences for this particular user code transaction. With shadow data, we don't need a persistent log. We can keep a volatile log just as an optimization, but and we do the actual modifications in place and flush them. So one flush for every modification first, and then at commit time, we have to do a fence, change the state that indicates that now it's the next replica that's consistent, and then again, we copy all the modifications to the other replica, flush those, and fence again. So this reduces to 4 fences and 8 flushes. Now let's talk about Trinity, which is the algorithm that we show on the paper. Trinity utilizes a kind of shadow data durability where 2 replicas of the data are kept in the same cache line. We call them main and back. We also keep metadata, which is just a sequence number, 64-bit sequence number. There's also one single word which we call PSEC, which is global metadata, and it's just a sequence number of the last committed transaction. Stores are interposed as we go along on the transaction, and we keep the old value on the back. We copy the old value to the back, and we write directly in place on the main the new value. So as you can see, when we did A equals 1, B equals 2, we wrote directly into the place for main. And we updated in the end the transaction number to be the new transaction number, which is 32. At commit time, we increment the PSEC, which is the global transaction number, to 33 to indicate that all transactions whose sequence is lower than 33 are committed and durable. Notice that the ordering of the stores is guaranteed by the PCSO model, so no fences are issued until the end of the transaction. If we go back to the example, what we see is when we do A equals 1, all we have to do is do the copy of the main to the back, set the main to the new value, and set the sequence equal to the P sequence. and then we flush this cache line. Again for B, and again for C. The loads are done in place. At the end transaction, we issue one p-fence to guarantee all previous stores have been made, and then we increment the global sequence, we flush that, and we do the p-sync for the final commit to guarantee all data has reached durable consistency. This means 2 p-fences and 4 flushes in total for this example, and there is no log neither in volatile memory nor in persistent memory. In our paper, we describe a second technique named Quadra, which has extra metadata in the cache line, namely 2 counters. This technique is a little bit more complex, and it cannot be combined with concurrency controls like TL2. But on the opposite, it can execute with a single flush per modification and a single fence in total. That means the p-sync. So this achieves the theoretical minimum of what can be done in number of fences. In this table, we compare different factors of these different durability techniques. And Trinity and Quadra both issue one flush per modification in the transaction, assuming these modifications occur on different cache lines and are random. If we compare that with a shadow data technique like Romulus log, it issues 2 flushes per modification, one on each of the replicas. And if we compare with a redo log like OneFile, it issues a little bit more than 1 on average, but you have to take into account that loads have to look up on the log, and that has a significant impact in performance. For undo log techniques like leap PMEM objects of PMDK, the average is 3 flushes per modification. Other factors come into play when you have to decide which persistent transactional memory to use. For example, undo log and redo log have an amortized memory usage that's proportional to the size of the log of the transaction. But if you want to do a transaction that goes over a significant amount of your whole data in persistent memory, then you need a log that covers all of that data, and so in the end you end up needing a maximum memory size, which is 4 or 3n, depending on the amplification on the log. We developed a second technique, which we call Trinity VR, where a volatile replica of the main data is kept in volatile memory, in this case DRAM, but it can also be in persistent memory, but it's volatile. So what this means is that as we execute the transaction, loads are done in place, and we can have variable-sized data types, so that means strings can be executed just in one go without having to be intersected by the back and the main as metadata. So what this means is that when we're writing to DRAM, and when we're reading from DRAM, and it's only at commit time when we end the transaction that the Trinity protocol is executed, and this data is copied from DRAM to persistent memory, updating the sequence numbers at each cache line, and finally the PSEC. Now let's talk about how to merge concurrency with this algorithm. When combining the volatile replica with the TL2 concurrency control, we keep the main components of TL2 in DRAM, in volatile memory. That means the array of blocks, the global clock, the write set, and the read set, those are kept in volatile memory. One extra change is needed in persistent memory for the Trinity algorithm, where we have one PSEC per thread instead of having a single PSEC. So we need an array of sequences with one entry per thread. The load interposing and the start interposing of the TL2 concurrency control are just the same as the original, except we use an undo approach with write-through execution. At commit time, we follow a protocol very close to the original TL2. We check if the transaction is read-only by looking if the write set is empty. We do read set validation, and only after the read set has been validated, we know that from a concurrency point of view, this transaction as committed. So now, and only now, are we going to replicate those writes on persistent memory. Up until then, it's all been done, all modifications have been done in volatile memory. We then increment the global clock, we do the durable commit using the Trinity protocol, and then we release the locks. The important point here is that first we do the durable commit and only then we make the transaction visible to other threads. So durability first while grabbing all the locks, and then we release the locks. In the abort, remember all the operations have been done solely on DRAM, so we can simply revert those using the typical TL2 approach and restart execution by calling a long jump. In case of a system crash, what we do is we execute the Trinity recovery protocol, reverting the last transaction if it's not committed, and then we copy the entire PM data into the volatile region, and we can start executing transactions from that point on. We will now study the performance of these techniques in the context of data structures. For the first of our micro benchmarks, we took the sequential implementation of a queue and wrapped it in a transaction. Each of these PTMs provides transactions that are concurrent and durable, therefore we use the same queue code for each of them. Now notice that this transaction encompasses not just the actual enqueue or dequeue, but also the respective allocation or deallocation of the queue's node, which means that in the event of a crash, the node will not be leaked and there will be no double free issues. The results show that Quadra with flat combining is the best, but Trinity is also a good contender. The reason why these techniques are better is again due to the low number of flushes that these algorithms execute. But in the case of Quadra, there's an extra advantage, which is when combined with flat combining, the multiple threads that are executing operations, their modifications on the allocator's metadata get kind of nullified with one another, because the allocations by one thread become allocations by the other, and so they touch the same metadata blocks, and the algorithm, the persistent transactional memory, is capable of aggregating and doing a single flush for those multiple modifications. In other words, it executes less stores to allocate or deallocate as a group, and this gives it higher performance. In this micro benchmark, we took a sequential red-black tree and we wrapped its operations in transactions. Perhaps contrary to what would be expected, the DL2 implementation here doesn't scale very well. And the main reason is because the red-black tree is a data structure which, for most mutative operations, the root node is modified. And that means that any operation that reads the root node, that means any operation in fact, will abort if there's an ongoing modification. And this causes contention and prevents scalability for TL2. If we took a zip tree, on the other hand, this no longer happens, and here the difference is really very noticeable. Even with just pure write-intensive workloads, as we see on the left side, 50% insertions, 50% deletions on the tree, we have very good scalability. The bottleneck we hit, we believe, is due to PM bandwidth. Similar results are seen for a B tree. Again, remember, this is a sequential B tree implementation for which we use the PTMs to provide concurrency and durability. Trinity is a persistent transactional memory, a PTM, and PTMs is just another name for database engine. Once you have a PTM that provides concurrent and durable transactions, you can use that to make a simple key value store. So key value stores, how they were done up until recently, is you take a concurrent indexing data structure, which has itself its own concurrency mechanism with fine-grained locking or whatever else it is, and you add some kind of two-phase locking mechanism for the records. Sometimes you add multi-version concurrency control. You add some kind of redo or undo log for the durability. Usually it's a redo log. And then you take several developers to glue this together and make the engine. And it takes some time, but ultimately you'll get the key value store. With Trinity PTM, what you can do is you take a sequential indexing data structure, sequential B tree in our case, and you add the Trinity volatile replica TL2 PTM, and then you have just some months of effort by a single developer, and you get the Trinity DB, a key value store with scalability for reads, scalability for writes, and durable linearizable transaction. Using the Trinity VR PTM, we created the Trinity DB with two variants, one where the concurrency control is given by TL2 and the other where the concurrency control is flat combining. Those are the green and blue lines in this plot. These are write-intensive workloads in the DB benchmarks, which are benchmarks created by LevelDB and later by RocksDB, also used by PMMKV. The override has the best scalability of them all because it has no allocations being done for reinsertions. Whenever the key is found, the value is just overwritten in place, so no further allocations. And allocations are costly because that means more writes. More writes means more flushes in the transaction. On pure random reads, flat combining wins because of the lower overhead. It just has to take one read lock and then execute its entire transaction with no extra cost in synchronization. It's very hard to beat that. And it's doing all of that on DRAM, which gives it a lot more performance than the other techniques. But on the read while writing, a single thread is doing insertions into the database in parallel. And that causes the performance to drop immediately because it's a global lock. For TL2, this doesn't happen. The performance is nearly the same because the TL2 concurrency control allows read-only transactions to execute in parallel with write transactions as long as they are disjoint. On this slide, we see a comparison for the Yahoo benchmarks, workloads A and B, where the workload A is 50% overrides, 50% lookups, and the workload B is more read-oriented with 5% overrides and 95% lookups. On the workload A, we can see good scalability up until 16 threads. We believe that beyond this point, we're saturating the bandwidth of the single Optane PM module that we have in our system. And perhaps more scalability would be possible using interleaved mode. The main insights of this work is that reducing the number of flashes to persistent memory is vital to have high-performance, durable transactions. And Trinity and Quadra algorithms do exactly that. They trade higher memory usage to have better throughput. And another insight is if you have enough DRAM available, then combining it with PM will yield the best performance possible. And even more, remember, you can take part of your persistent memory and allocate it in memory mode, which emulates volatile memory. So it acts as DRAM, and you can use that for your VR kind of algorithms. So you can pick and choose how much of your persistent memory is actually durable and how much of it is actually volatile. And concurrency-wise, well, if you have workloads that are mostly disjoint, then TL2 is the way to go. If you have things where the workload is really very serializable, like everybody's writing on a queue, then you're better off with something like flat combining. And RPTMs are implemented as a single C++ header with a bit more than 1,000 lines of code. And, you know, less code means less bugs. And a fast and scalable persistent transactional memory makes it easy to create a fast and scalable key value store. So that means you need that for a good database. Thank you.